I'm Josh Young. This lecture is on topography and wavefront. You can find more lectures at the resident level in ophthalmology, primarily in optics, at openophthalmology.com. You'll see that there are links there for an iPod, an iPhone app, and also for an Android app. And you can click up at the top of the screen at podcasts to get an archive of the 20 lectures. This talk is on topography, and as with a lot of the lectures that I give, the talk is based on food, specifically pizzas, bagels, and Schweppes Bitter Lemon, my favorite soda. When we think of measuring the shape of the cornea, we generally think about things like using the keratometer. And even though I'm going to be presenting different means of measuring the shape of the cornea, the keratometer is really important clinically because we use keratometric readings for things like contact lens fitting, and especially for things like calculating the appropriate intraocular lens power. Now, in our clinic, most of the keratometers that we're going to use are going to be what are called one-step keratometers, like the Reichert keratometer shown here, where the whole keratometer moves, and there are two dials, and we align the image properly, and we read the keratometric measurements directly from the machine once we've lined things up properly, meaning that we line things up properly and then we can copy down all the data that we need. Now, there's an assumption that this sort of keratometer makes, and the assumption that it makes, which is largely true for most normal corneas that have not had surgery, is that the meridian of greatest steepness of the cornea is orthogonal, is perpendicular to the meridian of greatest flatness of the cornea. And I'm going to represent to you that that's not universally true, and we're going to see some examples in which it is clearly not true. Also, if you look at the dials on the keratometer, you'll notice that there are two sets of scales. And I don't mean that one says horizontal, one says vertical. I mean that within each dial, there's a set of scales that'll go from, I don't know, maybe 36 to 49, and those are dioptric readings. And when we talk about the keratometry readings, those are usually the numbers that we're giving. We'll say that someone has, someone is 46.5 diopters at 80, and again, when we're using meridia, as we do with the keratometer, then we use the word at, in contrast to when we're talking about prescriptions, we're talking about axes, in which I don't let you use the word at. I would never let you say something like, someone is +3 -2 at 90. That would boil my blood. But with the keratometer, we really do use at, because we're talking about the meridia of the cornea anyway. Enough of that aside. You may give a keratometric reading of someone is 46.5 at 80 and 42 at 170. Now, those are dioptric measurements of the cornea, and they're derived, and to a certain extent they're fudged, and maybe we'll get to talk about that a little bit later on. But the measurements that are actually directly measured by the keratometer are the radius of curvature of the anterior cornea. And those are the other, that's the other scale on each of the dials. It may give a number like 7.65 or 7.2 or 8.0. Those are the radius of curvature. Obviously, larger values represent a larger radius, represent a flatter cornea. Anyway, next time that you're in clinic, you'll look for it. This is the other sort of keratometer that we use clinically, although it's unlikely that you're going to find this in clinic. It's a Javal keratometer. It's a two-step keratometer. And what I mean by two-step is that we'll get the measurements for one meridian when we line up the keratometer properly, and then we rotate the keratometer in order to get the other set of keratometric readings. And it sounds like it's a pain in the butt to use this sort of keratometer, and indeed it is. But it does not make the assumption that the place where the cornea is flattest is necessarily orthogonal to the place where the cornea is steepest. This is a little zoomed in view, and there are two different images that are projected on the cornea, and we line them up. I'm not going to go into precisely how this sort of keratometer works, but suffice it to say that we can have a cornea that, let's say, is steep at 90 and is flattest at 10. You'll never get a reading like that with the one-step keratometer like the Reichert that I showed you at the start. You can get that sort of reading with this sort of two-step keratometer. Okie doke. So what is a keratometer not going to tell us? Well, it's not going to tell us about a cornea like this, because the keratometer really only gives us two sets of readings. It'll give us a reading that, let's say this cornea, maybe it will give us one reading that's of interest at about the 120 degree meridian and another one at the 30 degree meridian. The problem is that the reading that it's going to give us at 30 may represent what the curvature of the cornea is at 30. But the reading that's at 120 is going to give us the average power at 120. And you can see that if you follow this cornea down to 290, that's to say in about the 5 o'clock position as we're looking at this cornea, it's very steep there. And if we go all the way up to 120, we see actually that the cornea is very flat there, and the keratometer is going to average those two out when it gives us the keratometric reading for the meridian of 120. It's not going to provide us with much insight about the curvature of this cornea. We need some other means to describe this cornea. By the way, what pathology does this cornea have? If I tell you that red means steep and that blue means flat, what is it that this cornea has? Speak up. That's exactly right. This is a patient with keratoconus. Okay. This is a Placido disc. Now, I don't know where the eponyms for these devices come from. I mean, this is a piece of cardboard with concentric circles that are black and white. But Dr. Placido obviously thought of this first, and Dr. Young came along later on, so that's why this is not a Young disc. But at any rate, it's a Placido disc. And the Placido disc has a hole in the middle through which the ophthalmologist looks, and the ophthalmologist brings this dartboard-like target up to the patient's eye and looks at the patient's cornea through it and sees the reflections, or if we want to be fancy, the first Purkinje images on the cornea of these rings, and will tell us by looking at the cornea, we can get a gestalt of the curvature in different parts of the cornea. This is a different sort of keratometer that we might use during surgery, and it also has concentric rings that, using the illumination from the microscope, projects rings onto the patient's cornea, and we can assess curvature like that. This is a Van Lunen keratometer. It is a clear piece of plastic with some bands of black and white on the inside that we illuminate from the side with a slit lamp beam, and we'll cast rings onto the patient's cornea. And indeed, when I started as an attending, I made the residents all buy these little rings. They're about $20 each, and they are very nice. They're regrettably fragile, but they are very nice. This is a Klein keratometer. It's the same thing as a Placido disc with the addition of two things. Number one, it has a light source so that the rings actually light up. And number two, it has right in the center, rather than a hole for through which the ophthalmologist will look, it has a plus lens which serves as an ad for the ophthalmologist for the very ancient ophthalmologists who have become presbyopic. I speak, of course, not of myself, and need to get very close to the patient's cornea and still be able to resolve the rings. Okay, let's take an aside now. You can close your eyes and picture this because I don't have any slides showing this. But imagine two steel balls. Imagine one steel ball that is very small, let's say the size of a marble, and is highly polished and is very nice. And imagine another steel ball that is the size of a basketball. And we're going to look at the reflections of ourselves in these steel balls because we like to look at ourselves. And in the case of the little marble-sized ball, let's say that the ball has a diameter of 1 centimeter, we can see our entire countenance in that 1 centimeter. And we look at the other one that's the size of a basketball, and we see the same sort of image, but it's spread over, I'll be honest with you, I have no idea how big a basketball is. Let's say it's 10 inches. Our image will be spread over the 10 inches of the basketball. Now, which of these two spheres is more curved? Which one has a more steep curve? Well, a more steep curve means a smaller radius of curvature, and it's obvious that a little steel marble is going to have a higher radius of curvature. A smaller radius of curvature is more curved than a basketball is. Now, how big is the image of us in each of these objects? Well, in the more highly curved marble, our image is smaller, and in the basketball, our image is larger. Now, picture this with the Placido disc. If we were to bring the Placido disc in the range of the little shiny marble and look at the disc through the little aperture in the marble, we would see all of the rings crowded into the size of the marble, the reflection on the marble. With the basketball, the rings would be much spread out. Or another way to think of it is that the distance between the rings, the distance, let's say, between two black rings with the intervening white ring, that distance in the basketball is going to be greater. The rings are going to be more spread out than they are in the marble. Well, the same thing happens when we look at a cornea, and this is the image that we might see when we look through a Placido disc at a patient's cornea. And the rings that are more closely spaced will indicate to us a portion of the cornea that is steeper, and more widely spaced will indicate to us a place where the cornea is flatter. And we can look at these rings and we can see, well, you know, the cornea is steeper here and it's flatter there. But here's a question. How much steeper does the cornea have to be for us visibly to be able to perceive that there's a detectable difference between the spacing of the rings? I'm going to leave that thought sort of hanging and let you look at this cornea and tell me, is this cornea regularly shaped? Does this patient have cylinder? If so, what's the axis of the cylinder? Does this patient have keratoconus? I mean, the rings all look pretty even to me, but what does it mean that they look even to me? Does that mean that the patient really has a spherical cornea? Well, this is someone who has a cornea that is clearly not spherical. Does this patient have keratoconus? Well, we can see that the rings are kind of ovoid in shape centrally. But we can see that there's this sort of tight grouping of the rings inferiorly. You can see that not in the center, but a little bit south of the center, that the rings look very crowded, that the spacing is very, very close. Whereas, let's say that this is the patient's, I don't know, left eye, so that the nose is to your left as you're looking at this image. We can see that the spacing, that the gap between the rings on that nasal side is really very wide. Whereas the gap between the rings inferiorly, particularly infratemporally, is very narrow. The rings are very tightly packed. So infratemporally, this cornea is very steep, and nasally, supranasally, this cornea is very flat. This could easily be a patient with keratoconus. There's a problem with Placido disc images. There are several problems. One of them is that they're not quantitative. Even as they give you a sense of the curvature of the entire cornea, they do not give you any quantitative data. But the second one is that they're ephemeral, right? What are you going to do? Start drawing rings in the patient's chart? So we need some way to document the distribution of the rings on the patient's cornea. And someone had the bright idea of mounting a Polaroid camera, an actual Polaroid camera, on the back of a Placido disc. And this is what a photokeratoscope is. When I was growing up, when I was a fellow at Mass Eye, there were charts with Polaroid pictures of Placido disc images stapled into the patient's charts. And you say, well, Josh, I didn't know in your days they even had staples. No, but it's true. We had staples and real paper and Polaroid pictures stapled to the charts. Well, that's well and good. We can see the rings and compare them in a kind of a gross sense, but there's nothing quantitative here. And we still haven't answered the question, how distorted do the rings have to be for us as observers to say, well, I can recognize that this portion of the cornea is steeper, this portion is flatter. So this is, what a photokeratoscope image might look like. And again, I ask you, does this patient have a spherical cornea or not? This is another sort of intraoperative keratometer. And what it is that you hold this ring over the patient's cornea, and you look at the reflection of the ring on the patient's cornea. And of course, like all the other keratometers that I show you, you have to make absolutely sure that you're holding this ring parallel to the floor. Otherwise, if you tilt the ring a little bit, then you're going to recognize a cylinder that's not there. The reason that I show this pictures is this. You see that circle that's etched in it that says 2D and the one next to it that says 4D? Well, that 2D ring, that's what 2 diopters of cylinder looks like. Now, how round does that ring look? I mean, to me, that thing looks pretty round. If I were to see this, and you can even sort of tilt your head to double check this, I'd have a really hard time judging where the axis of that cylinder is. Okay, the 4 diopter one, I can recognize that that's ovoid. And indeed, I think that it's pretty reasonable to say that you need about 4 diopters of cylinder for you to visually recognize that something is an oval and not a circle. So the photokeratoscope images are nice in that they provide a sense of the whole cornea, which the keratometer does not do. But someone really has to have substantial cylinder for you to recognize it, looking at the rings, or of course looking with a Placido disc or a Klein keratometer or a Van Lunen keratometer or anything like that. Okay. Well, in the mid-1980s, J. James Rousey in the University of South Florida had an idea that was very clever. These images are not his, but they're a good way to think of things. He photographed a bunch of little steel spheres, just like the steel marble that we were talking about when we were looking at ourselves. And he took photokeratoscope images, and he measured, actually, of course, he didn't measure, right? He had his residents and fellows measure. They would actually take rulers and would measure the distance between the rings for steel spheres of known radii, and created a kind of a table, a lookup table, that said, okay, well, if the spacing of a ring is this number of millimeters on the photokeratoscope image, then that means 45 diopters at that point. Well, so you could then take a photokeratoscope image, and you could produce a quantitative map if you had a fellow who had an entire day to do it. That was well and good until Steve Kleiss came up with the idea of using a computer to do the same thing, where the computer had the lookup table stored and would detect the ring borders and would measure them and compare them with the lookup table, then generate this sort of color-coded map. And using the color coding scheme that's been used since that time, red means steep and blue means flat. What about this cornea? This is an interesting cornea, right? So this cornea has in the mid-periphery an area that is very steep, and in the center an area that's very flat, and in the periphery an area that's very flat. So what's going on with this cornea? What do you think? Well, you could say, well, could this be radial keratotomy? Because radial keratotomy produces mid-peripheral steepening and central flattening. I credit you. That's a good thought. I'm glad you suggested that. But no, this is an intrastromal ring, and the cornea is steep at the area of the ring and is flat centrally. Okay, and this is a picture of an early computer video keratographer topography unit that took the Placido disk images and calibrated them. Okay. As you know, those of you who know me, I would like to say I'm a foodie, but let's just say I'm obsessed with food. And food plays a big part in this lecture. So let's get on to our first food stuff. So this is a can of soda, and it's a cylinder. And corneas can have cylinder too. Of course, corneas are spherocylinders. They're not just straight cylinders. But we're interested in that portion of the cornea that part of the curvature that is a cylinder in an astigmatic cornea. So let me ask you this question. This can of Coke, in the position in which it's sitting here, is with the rule or against the rule? Oop, let me get the phone.